Welcome everyone, it's Mr. Smith, and this is a video all about some new calculus-related topics. I understand you're not in a calculus class, but it is pre-calculus. And what we're going to do is we're going to explore some new topics called limits, continuity, and end behavior. And later on, as we learn all kinds of new functions and get reintroduced to old ones, we're going to start weaving these calculus topics in so that calculus will seem like a breeze to you down the road. So the structure of what we're going to do today, there's a couple of introductions we'll do over the course of this particular video with some definitions and ideas. And then we've got a couple of level 1 examples along with a level 2 example. So I'll have you pause the video. If you're done, you're like, hey, that's a lot of information. That's all I need to know. All right, you can pause the video or move on with the video. But here we go. So our first concept is the idea of a limit. And you have to imagine what's happening as x approaches some sort of a value without necessarily reaching it. So I've got this graph of a rational function. You may have talked about functions like this previously in earlier classes. So this function's got a lot of problems with it. Particularly one problem as we're approaching -2. You see this hole in the graph. Well, as we're approaching -2, you'll notice that the function wants to reach a certain value. That value that we want to reach is what we call a limit. And it looks like this function is trying to reach a limit of -1/3, even if the function value doesn't ever actually get there. All right, so the limit we say is -1/3. And here's our notation right here. LIM stands for limit. And this is saying as x goes to -2 of f of x equals -1/3. As we get closer to 1, you'll notice that we don't seem to approach any one value at all. It's not a unique function value. In fact, we're going to negative infinity, it looks like, as we approach the left side of 1. So that's how we would call that. And we're getting closer and closer to positive infinity as x goes to 1 from the right. So if there's no one single value that we're approaching, all right, we say the limit does not exist, or DNE. We also have a situation of a DNE limit as we're getting closer to 3, okay? So as we get closer to 3, from the left side, it looks like the function's getting closer to 0.5, all right? That's the y value that we're getting closer to. If we look as we're coming in from the right side of x is equal to 3, so values that are a little bit bigger than 3, like 3.01, 3.001, 3.0001, it looks like our y value is getting closer to 1. And since we're not approaching a single unique value like we were over here, we say here that the limit also does not exist. All right. So the limit is that unique function value that we're approaching. It's kind of important to say that this function approaches values for all the other values in its domain. So for example, if x is equal to 0, it looks pretty clearly like the function's approaching -1. And it just so happens that it reaches -1. It fulfills its intentions. It does what it says it's going to do. All right. As we're going forward, we're going to identify these weird parts of this function as points where we're discontinuous. So to back it up just a second, we're going to say a function's continuous at x is equal to c if it has no breaks, holes, or gaps. And the way that works is if 3 things happen. If the function value exists, f of c, if the limit exists, and if the limit as x goes to c of f of x equals f of c. So one place where we're continuous, where we have no breaks, holes, or gaps, would be at x equal to 0. So if you see right here, what's happening is f of c exists, so f of 0 exists. There's no hole in the graph. The limit as x goes to c of f of x exists because this function is trying to reach -1. And the limit as x goes to f of x of f of is equal to f of c. All right, so this function reaches the value that it's supposed to at x is equal to 0. Opposite term is what we call discontinuous, and we see 3 different types of discontinuity in this particular graph. All right, this type right here where we have a hole in the graph is what we call removable discontinuity because it looks like we just removed a portion of the graph right out. The limit and the function value exist, but they don't equal each other. In this case, the function value doesn't even exist at all. We have an infinite discontinuity, x is equal to 1. In this case, the function values are decreasing or they're increasing without bound. And then we have a jump discontinuity right here at x is equal to 3 because the limit as you go from the left doesn't match what's happening from the right. You have two distinct values. So these three different types of discontinuity we're going to see. Now what you're going to do as you're investigating these with your homework is perhaps create a little table of values, which we'll see an example of in just a second. But the idea is to figure out, well, what is the function approaching and does it actually reach that value? And we'll prove there that the function's continuous. You're not going to do too much with the fancy algebra that you would in a calculus class. So here's an example. Identify points of continuity or discontinuity, this function right here. Now we don't need to know what the function is, but what we're going to do is we're going to create a table of values and look at values around x is equal to 0. All right. So what we would say is, yes, f of 0 exists. That's equal to -1. And the values around x is equal to 0 approach -1 as well. So this function is continuous at x is equal to 0. All right. This function reaches what it wants to reach. On the other hand, is the function continuous at x is equal to -2? We would say no. So notice that my function values around -2 look like they're approaching -0.333 or -1/3. However, when I plugged in -2, I got an error. This is what we would call a removable discontinuity. It looks like we're trying to reach -1/3, but we get an error here. The function continuous at x is equal to 1? Well, we would say no, because look at what happens as we get close to 1. These function values are getting higher and higher, all right, even close to 1,000 or -1,000 on either side. So these values are growing without bond, and they would grow even farther if I had numbers that were closer to 1. We call that an infinite discontinuity. The function continuous at x is equal to 3. All right, well, we would say the function values to the left of 3 are getting closer to 0.5, while to the right of 3, our function values like 3.001 or 3.01 or 3.1 are getting closer to 1. All right, so what's happening here is we're trying to reach two different values at one point, as you can see with the graph. So we say this is a jump discontinuity. All right, our other term that you're going to need to know from this particular video is what's called end behavior. And the end behavior of a function describes how the function behaves as x increases or decreases without bound. All right, as our x values get really, really large and we say approaches infinity, or as the x values get really, really small and approach -infinity. And our notation for that is the limit as x goes to -infinity of f of x, that's decreasing without bound, and the limit as x goes to +infinity of f of x. We could get a value for this, or we could get an infinite value for this. So for example, let's say we have the graph of f of x is equal to x cubed plus x squared minus 3x minus 3. What we notice if we were to do another little table here is as x decreases without bound, as we go to the left side of the graph, the function is also going down to -infinity. Our y values go way, 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 way down. In fact, as x is -100,000, our y values are close to -10 to the 15th. Really, really low. So the way we would write that is we would say limit as x goes to -infinity of f of x equals -infinity. As our values increase without bound, all right, as we see right here, we plug in larger and larger x values. They get higher and higher. We approach something like 10 to the 15th, and they would get even higher as we go along. So we say as x increases without bound, f also increases without bound. And our notation will be limit as x goes to infinity of f of x is equal to +infinity. Okay. However, we could have some sort of a graph where we're approaching values. So if we did another table of values for this function right here, absolute value of x minus 4 over 2x plus 1, we see as x decreases without bound, our values, so as we're going negative and negative and negative and more negative, like in this table, our values get closer to -1/2. So we say limit as x goes to -infinity of f of x equals -1/2. As x increases without bound, our function approaches +1/2. And we can see that in our table here. Increases without bound means our x values are getting larger and larger and larger, and our y values get closer to 1/2. So we say limit as x goes to infinity of f of x is equal to 1/2. All All right, you can pause the video right here if you are good with the level 1 items. If you're going to continue on, there's one more little topic we're going to talk about. All right, one more calculus topic we'll talk about is what we call the intermediate value theorem. And for now, the idea is this. If we have some sort of a function that crosses the x-axis, we'll know that on one side the function was positive and on the other side the function was negative. And this is true for what we call a continuous function. As an example, I give you f of x is equal to x squared minus x minus 3. And I did a little table of values here which show me what my values are for this function. So the idea of this theorem is to figure out where our zeros for the function are located. Clearly the function is not equal to 0 anywhere in this table, but we've got some other interesting things going on once we make our table of values. And if you notice, in between x is equal to -2 and x is equal to -1, there's a sign change. All right, and since this is a polynomial function, this is going to be a function that's not going to have any breaks or holes in it, and it's going to be what we call a continuous function. So in this case, there's a sign change between -2 and -1, and x is equal to 2 and x is equal to 3. Notice the sign goes for y from negative to positive. So in that case, we know since f is a continuous function, there has to be a 0 somewhere in between, that this function has to cross the x-axis. All right, so if we were to take a look at a graph, it makes that a little more clear of what's going on here. So here's the graph of our function right here, our quadratic. And we can tell what's happening is in between -2 and -1, our function went from a positive number to a negative number with its y value. So there's some sort of a 0 in between. We don't know necessarily what it is unless we did something like the quadratic formula, but this is a quick and easy way to see where our zeros might be. There's also one between 2 and 3 because our function went from a negative number to a positive number in between 2 and 3. And we call this function the intermediate value theorem. All right, studied more in calculus. So this is the concept where we also might call this the location principle. So for our purposes, that means that if our function is continuous and f of a and f of b have opposite signs, there's some sort of a 0 between a and b. All right, in summary, you've been introduced to terms of calculus, limits, continuity, and behavior, intermediate value theorem. You're pretty much like got a lot of Unit 1 ideas right out of the way for calculus, but we'll be seeing them throughout our pre-calculus careers here. And these terms will also be useful in describing what a function is doing and what a function looks like. So more on that later on. Thank you for watching. We'll see you on the other side.